Welcome back to this channel. In today's video, we shall demonstrate how to calculate the center of mass of solid bodies. What do we mean by solid bodies? Examples include a rod with certain mass, with certain length. So if this rod is, let's say, uniform, meaning the density of this rod is a constant, where is the center of mass for such a rod? Other examples include a plate like that. Let's assume it is a square plate with sides L and mass M, and maybe the density is not constant. How do we evaluate the center of mass for such a body? To best illustrate the technique, let's look at the following problem. A thin rod has a length L and mass M with cross-sectional area A. Locate the center of mass of this rod if its density is constant. So let's look at part A first. So this essentially is a one-dimensional object. I'm going to align this rod with the x-axis. I'm going to put one end at the origin. The length of this rod is L and the mass is M. Now the cross-sectional area is A. We are told that the density is constant. Now we are doing part A. So when density is constant, density equals the mass over volume. Mass is M. Volume is just the cross-sectional area times the entire length. Let's assume that we want to identify the center of mass using this coordinate system. So the center of mass is somewhere along that x-axis between 0 and L. So to determine that, let's look at one sliver of that rod. The length of this segment is dx, and it contains a mass of dm out of the entire mass, capital M. Also, let's assume the coordinate or the position of this element measured from the origin is x. So the center of mass for such a body equals the sum of terms such as dm times x over sum of all the masses such as this one. Because this is a continuous solid body, when we say continuous, the distribution of mass is continuous, it is not discrete. So the sum simply becomes an integral. So the one on top is quite simply x dm. It's an integral in the variable little m over an integration over dm. But the denominator is quite simply the total mass of the rod. So we can substitute that in, and you get an expression x dm over capital M. Now from this expression right there, M is quite simply the density, which is constant, times the cross-sectional area times the length of that rod. So let's substitute that in here, rho AL. Note that the integral has a variable in m, but this is x. M also varies with x, so we need to figure out an expression of m in terms of x. In order to do that, let's look at this element again. Now we know the density of this entire body is constant. Density equals mass, if we apply that equation to that small element in red, over volume. Volume is A times the length of that element, which is dx. So there we have it. dm equals density times cross-sectional area times the length of that tiny element. So let's substitute this expression in there, which will give you density times the cross-sectional area times dx. Note that density is a constant, cross-sectional area is a constant, and that can be taken out of that integral sign, giving you rho A integral of x dx over rho A L. That is that term. You see, rho A will be cancelled by the rho A at the bottom, and this integral is easy to do. This is x dx. The denominator has L there. Now let's look at the limit, the lower and upper limit of this integral. It starts from there, ends from there. Such an element extends from x equals to 0 all the way to the other end where x equals to capital L. So those are the limits, 0 to L. So this integral is easy to do. Half x squared. We have to put in the limits over L. So that means you have half L squared over L, and giving you the answer of L over 2. So that is the coordinate of that center of mass. For such a uniform rod with constant density, the center of mass is exactly in the middle. Now let's look at part B. Repeat the calculation if the density now varies linearly with x. So the expression for density is given by that. This A is a constant. In this case, the density is a function of that x coordinate, like that. We do the same trick. We divide up this entire non-uniform rod into such tiny elements, and the width of that is dx. It contains a mass of dm, and the location or the x coordinate of that element is x. So the center of mass, as before, can be written in terms of integral x dm over an integral dm. We again note dm over the volume. The volume is A times dx equals the density. Thus, dm equals rho cross-sectional area times dx, and we can substitute that in here and in there, which will give you the following form: rho A dx, rho A dx. A is a constant that can be taken out. Rho is x dependent. So let's substitute that expression. It is ax, ax. However, a is a constant. The little a is a constant, and that will cancel out. So you get the integral of x squared dx over the integral of x dx. Now note the limits from 0 to capital L, 0 to capital L, 0 to capital L. The integral on top is pretty easy. It's going to give you 1/3 x cubed, putting in the limits 0 to L, over the one in the denominator is half x squared, again 0 to L. So let's simplify this. The numerator will give you L cubed over 3, and the denominator will give you L squared over 2, which is L cubed over 3 divided by that, or times 2 over L squared. So that's going to go away, and the final answer is 2 over 3 L. So that is where the center of mass for this particular rod is. It is located at a point which is at a distance of 2/3 of the length measured from the origin on the left. As always, thank you for watching.